Hey everybody, Dr. Retzig back with you here. This is our 7th video in Math 406, and it's a continuation of our discussion in section 6b of orthonormal lists, Gram-Schmidt procedure, and today's discussion is about consequences of Gram-Schmidt. So we are still in section 6b. It's a continuation of that discussion. And it's all about consequences of Gram-Schmidt. Now, the first thing I thought we could do is kind of discuss the upshot of the example in the book. There's a really nice example on page 184, which is all about this picture. In that example on page 184, you got the vector space P2 of the reals. So this is all polynomials up to and including degree 2 with real coefficients, and it's equipped with an inner product where the inner product of P and Q in that example, it's like one we've been using, but the limits of integration are slightly different. Anyway, it's integral minus 1 to 1, P of x, Q of x, dx. So this thing is an inner product space. Now, in that example, they basically come out and say, all right, you guys know your favorite basis for P2, and it's easy to write down. There's a constant function 1, polynomial x to the first, and polynomial x squared. That's what most of us would consider to be the standard basis for this space, and certainly any quadratic can be expressed as a linear combination of those. So it's a nice basis. It's great. That's the one we used all last quarter, I suspect. Okay. Gram-Schmidt says, though, oh, if you want to turn a linearly independent list, which this is, into an orthonormal list, like new and improved, you just follow the algorithm and you just gut it out. And that's what the example on page 184 is doing. I want to write down what happens. We're not going to do the computations. You can read them. You should work through them to make sure that you have the mechanics of Gram-Schmidt down. But what happens is this. When you take these and you Gram-Schmidt them, it improves them to an orthonormal basis. That process results in constant function 1 over root 2, linear function root 3 halves times x, and quadratic root 45 eighths all times x squared minus a third. And this basis, this one that Gram-Schmidt has produced, is orthonormal, whereas the original one is just a standard kind of linearly independent basis. Now, a natural reaction to that image is to say, you really messed up our nice basis. Like, what? Why would you do this? Stop that. We were all perfectly happy with the basis 1x x squared. Yeah, I'm with you. That basis is great in many ways. But remember, orthonormal lists are particularly nice for computations. So even though the basis vectors look scarier on the right, they're definitely a little cleaner in a computational sense because they're orthonormal. So the inner product of any of those with the other is 0, and if you had some linear combination of the ugly basis, you would immediately know what the norm of that linear combination was just by looking at the coefficients by Pythagorean theorem. There are lots of virtues to having this orthonormal basis, even though it's not as easy on the eyes. Anyway, you guys should work through that example and make sure that you can reproduce all of that computation and just sort of grind out Gram-Schmidt when you have to. The remainder of this video is about listing some consequences of Gram-Schmidt. So these are theorems like 6.34 through 6.38, and I think this goes all the way up through page 186. I want us to just write down these theorems and check in with each other here on the video about why they're true. So let's just start the long list and say, all right, here's theorem 6.34. Okay, this one says, every finite dimensional inner product space has an orthonormal basis. Every finite dimensional inner product space has an orthonormal basis. So all that's being said in this theorem is encapsulated in this picture. So you have a vector space. It's equipped with some kind of inner product. Nothing specific. I mean, we don't know what this thing is. It's purely abstract. And it's finite dimensional, which means, by definition, there's a basis of finitely many vectors. So let's say you had a basis like this. V1, V2, through Vn. So that's just n objects in that box that are linearly independent and span the entire box. So anything in there can be made out of those by linear combination. And now the theorem is just immediate. This isn't a meaty, complicated thing. If you believe in Gram-Schmidt, then all you have to do is take this linearly independent list, Gram-Schmidt it, and that will produce an orthonormal list, same number of vectors on it, only now the e's are orthonormal. And remember, the bonus feature of Gram-Schmidt is at every step along the way, you don't change the span. So that means this new list, E1 through En, still spans the whole box. And since it's got n things on it, which is the dimension of V, it's a basis. And that's it. That's what theorem 6.34 says. So anytime you have a finite dimensional inner product space, you can just say, and assume E1 through En are an orthonormal basis. There's always an orthonormal basis, courtesy of Gram-Schmidt. Okay, here's theorem 6.35 in the book. Theorem 6.35. This one says orthonormal lists extend to orthonormal bases. Okay, now there's a subtlety in the semantics of that statement. The image that goes with this one is like this. You got a big box V. The fact that they even say the word orthonormal means they are tacitly telling you that this thing's an inner product space. You would never say that word if there were no inner product. So this box is equipped with some kind of inner product. Again, it's abstract. Nobody said what the inner product is. Nobody even said what the box was. This is just a big box of stuff with an inner product on it. The statement in 6.35 is that orthonormal lists extend to orthonormal bases. Okay, now let's be clear about this. They're saying if you start with an orthonormal list, say E1, E2 through EM, that is supposed to extend to an orthonormal basis, meaning there are supposed to be some additional vectors we could tack onto that list to make the list a basis and still orthonormal. So here's the line of reasoning. You bust out Linear Algebra 2, Math 306, and you say, okay, well, since orthonormal lists are Li, E1 through EM, they definitely extend to some kind of a basis. So let's say you have to tack on F1 through Fn. So now that collection there, having tacked on those extra few vectors F, this is a basis. Now that it's a basis, you go back to the previous proposition and say, oh, okay, well then Gram-Schmidt that and extend it, or sorry, change it into an orthonormal basis. Now something magical happens here. If you do Gram-Schmidt and the first few vectors on the list that you're doing Gram-Schmidt to are already orthonormal, then Gram-Schmidt doesn't change them. They're already unit vectors. They're already perpendicular to each other. So through the first m steps of Gram-Schmidt, literally nothing happens. Those are the exact same vectors. Now, once you get to the orange ones, which weren't necessarily orthonormal with the rest, remember, they were just tacked on to make the original list a mere basis, not necessarily orthonormal. All right, then Gram-Schmidt might be actually, chewing on some stuff and turning those orange ones into some better additional vectors, say F1 hat through Fn hat, where now the new list is orthonormal. And again, since the new list is orthonormal, it's linearly independent in particular, and since it has the same number of things on it as the original list, and the original list was a basis, then the new list is too. So 6.35 says if you start with any orthonormal list, even if it falls short of being a basis, you can extend it to a basis, you can turn that basis into an orthonormal basis, and the first few vectors on the orthonormal basis will be the same as those first original vectors you started with. Anyway, zoom out, see the forest. Despite all those trees, this says anytime you have an ON list, you can turn it by extension into an ON basis. Okay, next consequence. It's just like a greatest hits list. So now we have theorem. Oh, well, I want to go in black here. Now we have theorem 6.37. So this is all happening in 6b. These are all fancy consequences of believing in Gram-Schmidt. Next, you remember last quarter when we studied upper triangular matrix representations? Theorem 6.37 is about those upper triangular matrix representations, and it says something like this. If the matrix for a linear operator T turns out to be upper triangular for some basis, then there is an orthonormal basis that makes M of t upper triangular. And I want to be clear in our notation. The upper triangular version of M of t with respect to the orthonormal basis isn't the same upper triangular matrix. It could have totally different entries, but it's upper triangular nonetheless. So I don't know if we shouldn't use asterisks or something. I mean, maybe we should use like hash marks. There is no suggestion here that the two matrices are the same matrix. All we're saying is, if you find a basis, any basis, that makes M of t upper triangular, then you can definitely find an orthonormal basis that makes M of t upper triangular. The rationale goes like this time. Say you had a basis, some random basis, you know nothing about it except it makes M of t upper triangular, like here. So say you found a basis that made this happen. Well, you can do Gram-Schmidt to that basis, and that will definitely turn it into an orthonormal basis. The question is the matrix with respect to the new orthonormal basis still upper triangular? And the key thing is, you guys had a characterization of when a basis would make a matrix upper triangular, and I think the characterization was at each step of the way in the basis, the span of the first however many vectors in that basis had to be invariant under t. That's why you're getting zeros below the diagonal. So in that column right there, it's all zeros below the diagonal, because when you do t to v7, you can write it as a combination of v1 through v7. You don't need any v8 onward. It's all zeros from v8 onward. And the beauty of Gram-Schmidt, remember, that bonus feature in Gram-Schmidt, at every step along the way, you don't change the span. So if the span of v1 through v7 is invariant under t, then the span of e1 through e7, which is equal to the span of v1 through v7, is still invariant under t. So you still get zeros in that column from 8th slot onward. Anyway, zoom out again. All it says is, if you can find a basis that makes your matrix upper triangular, then you can definitely find an ON basis that makes your matrix upper triangular. And then a corollary of this is the last result. It's Theorem 6.38. It's a corollary to this. Some people call this Schur's theorem. Theorem 6.38 just says, if V is a complex, finite, dimensional, inner product space, and the word complex is key right there. Then M of t is upper triangular for some orthonormal basis. Let's make sure we're clear on the logic here. The previous result said, if you can find any basis that makes your matrix upper triangular, then you can find an ON basis that does. Down here, we added the hypothesis that this is a complex finite dimensional inner product space. And you guys know from last quarter that in a complex finite dimensional vector space, you can definitely find a basis that makes your matrix upper triangular. And once you find a basis, you can definitely find an ON basis. So complex finite dimensional inner product spaces are especially nice. You get to just say, anytime you're in that setting, you just get to say, oh, let E1 through En be an orthonormal basis with respect to which the matrix is upper triangular. You can just say that anytime you want, because it's always possible to find such a basis when your inner product space is complex finite dimensional. Okay, so all we really did today was we kind of went through what Gram-Schmidt purchases for us, and we get a bunch of theorems that are sort of improvements of things that we had last quarter before we had the structure of inner products. All right, that's it, I think, for Gram-Schmidt. And moving on for Monday, we're going to continue our discussions in Chapter 6. All right, see you next time.